right, good afternoon. We're going to go on and talk about depositional environments today. Just wanted to point out that if you send me an email, please include what class you're in and the section, because I get an email that says, "Oh, when's this assignment due?" If I don't know what section you're in, then I can't tell you because it's different for each course and section. Okay, so it just saves me having to go through all my class lists trying to find your name, or sending you an email back and asking you. So it's just helps to save a little bit of time. All right, do we have any questions? Yes. I think I set it for 2. I think. I don't know. Moodle, setting these quizzes up on Moodle is really kind of complicated. It's very time consuming, so there's a lot of different stuff you can do within these quizzes, and I don't even know what half of it means. So I think there was 2 attempts that I set it for. Any other questions? All right. iClicker. Do we have any more? Good job. Remember, you can get fossils in metamorphic rock, but they're going to be deformed, misshapen, and stuff like that. So they're not really very useful to us. We can't get them in igneous rocks. Why not? Not typically. Yes, because it's lava. If you think about lava being, I don't know, 1,000 degrees C, if it were to flow over an animal or a body, what's going to happen to that body? It's going to be incinerated. So we typically don't find fossils. Occasionally you can get a waterlogged tree which lava flowed around, and because it's waterlogged, you'll get the tree sometimes fossilized, but it's not all that common. Okay. So, some introductory stuff here, which we've already talked about a little bit. Remember our lithophases and our biophases. These are just different forms of the idea or concept of this facies, which is a sedimentary unit having a set of characteristics in common and particular to a local environment. Okay, and by local we mean kind of a large area, but mappable in that those items are mappable within that area. The biophases expands on it with, in particular, its fossil content. So it's an assemblage of fossils in these faces, which are then we can map them, tie them together, correlate them. Okay, hopefully you remember something from physical geology about grain size, sorting, and roundness, and how this relates to transportation. So if we pick up a sandstone, okay, we can look at the grains in it, and we can say whether they're rounded, whether they're angular, whether they're well sorted or poorly sorted, and that's going to tell us a little about how far that sediment was transported. Okay, so the relationship is basically that when we're up in the mountains, for instance, the rocks are weathering, and then that erosion process begins, start to transport it. The particles are typically going to be bigger, and so they're going to, as they move down, they're going to break down, right? So we start out, let's say we start out a chunk like this, a hand-sized chunk of rock. As it goes along, it's going to be, it's moved along the bottom of a river up in the mountain, it's going to be slamming into other rocks. And that's going to cause them to break apart. They're going to break apart into smaller and smaller pieces. But it also is going to round that particle. The sharp, jagged edges are going to be knocked off. And so it's going to become smaller and rounder and typically more well sorted. Okay, here's our relationship. So we can see we've got very angular over here, lots of sharp, jagged pieces on it. Those are going to be knocked off the more it's in this river system and bouncing and hitting on other rocks. And so by the time we get, if we would go down to somewhere like Grand Isle and look at the sediment down there, we would see that it's very, very rounded. It's sand-sized, and so they're all about the same size. We call that very well sorted when they're not a very wide range of particle sizes. Okay. As I click there. Do we have any more? Good job. Long distance. Okay, some other things we're going to look at. Bedding. Bedding is simply this layering that we see. This was once sediment, so a layer of sediment was built up over time and eventually got buried deep enough that it underwent, it was turned into a rock from a sediment. So we had compaction, cementation occurring, and we end up forming these beds. Now beds can be really, really thin, or they can be really, really big. Some beds can be tens of meters in thickness. Bioturbation, simply a reworking of sediment by organisms. So if we go out here, right now we've got lots of mud near the surface here, and we dug a little hole. We'll probably see some worms in the soil, some different organisms. You have burrowing mammals out there. Well, that changes the soil characteristics. It moves it around a little bit. So we lose some information in that sediment, but we also are able to have get some other types of information from this. Okay, ripple marks. Ripples are very, very diagnostic. We have two kinds, symmetrical ripples and asymmetrical. Now, what this indicates is direction of flow of current. And that can be very, very important if we're trying to figure out what kind of environment we're in. If you see here, we have these symmetrical ripples. They're equal on both sides. Now, what does that tell us about current direction? Well, it tells us that we're going to have two directions. Now, you can't have water flowing two directions at the same time, right? So, where do you think we might be able to see water where we get one direction followed by another direction? Beach. Beach environment. Those waves come crashing up onto the beach, and then that water runs back. So we've got two directions of current. So whenever we see these symmetrical ripples in conjunction with other stuff, we can be fairly certain we may have a beach. Okay. The other ones, asymmetrical, indicate that we have one direction of current. Where do we get one direction of current? River. Okay, so these can be very diagnostic. However, I will point out, I have some here. These are genuine ripples. Um, can you tell whether they're asymmetrical or symmetrical? It's kind of a little difficult to tell sometimes. But these are actually symmetrical, so they would have been formed on a beach. And one of the things you have to start learning to do is looking at all the information. So you look at the rock type, you look at the fossils that you're getting in that area, right? Make sure you include all the information. You want to get as much information out of these rocks as you can. Okay, some other things you might see, cross-bedding. Remember, this is where we get deposition over here, and so the actual bedding plane would be like this. So we get this diagonal layering within a bed. We can get graded bedding. This is very indicative of an energy decrease. So what happens, if you remember how energy in water relates to deposition, if you've got a very low energy water, kind of like our bayou out here, then it's only going to be able to carry very, very small particles, so mud and silt particles. It won't be able to carry sand or anything. However, if you get, like up in the mountains where you've got very high stream gradient or flowing over a relatively steep slope, that water's going to have much more energy. It's going to be able to carry much bigger particles. So, what does it tell us if we have graded bedding, which we have a bed something like this, and then we got big particles on the bottom, and then as we move up, they get smaller and smaller and smaller. What does that tell us? It tells us that we have high energy here, okay? Then as we go up, that energy decreases. Okay, so that can give us a clue. Where are we likely to see something like that? Where do you get a very high energy, or I should say, what kind of event? Get very high energy water, then it slowly decreases. Well, what is the cause of energy in water? Well, if it's flowing down a steep slope, right, that can have a lot of energy. Can you change that slope? No, slope's never going to change, right? Not in our geological instant when this bed was formed, okay? So we can't change the slope, so we know that something else must be going on. How about a flood? If we have a flood, we know all about floods around here, right? We have very high energy water to start with, but then it's going to slow down. As that water passes through, we're going to slow down, and it's going to go back to just carrying silt and mud. Okay, so these are good for that. We do get these graded beds in other events. Okay, there's something called a submarine fan, where sediment will build up on the edge of a big slope offshore, and then every now and then it will slip and go down really, really quickly, and all this sediment, the bigger particles are going to settle out first, and then followed by the smaller particles. Mud cracks. Mud cracks we talk about in physical. I have some here preserved in this rock, which I'll pass this around so you can get a closer look. You should be able to see that you've got these cracks in there, and they go through onto the other side. Now, these are raised a little on this side. These are indented. So which way was up? The indented side? If we think about our mud cracks, I'll just go forward to a picture here. Okay, we got mud cracks. So this is the surface, right? So that is the indent that we see here. Other sediment flowed in here, was deposited over the top, but it's a weakness area. So this is basically a bed, okay? And if you imagine this was sitting on some other ones, right? So if we put it on, the indentations are going to be in those cracks. So that tells us which way up this was, okay? Yeah. All right. Now, that is actually a really good example of what we call a geopedal structure, which allows us to tell the younging direction of strata. What does that mean? Well, remember our relative dating? We had a law called superposition, where the oldest is on the bottom, youngest is on the top. Now, there are certain situations that we can get where we can actually take a sequence of rock and turn them over naturally, okay? Now, if we go out and we want to know which is the oldest, we have to have a way of telling which direction was originally up. And these geopedal structures can tell us that. So, these mud cracks, we can look at it and we can tell which way was originally up because the mud cracks make that little indent in the top. Very, very useful. How can this happen? Well, if we think about folding, we know that if we bury rocks really deep, we can fold them. Well, what can happen is you can end up with this recumbent fold where it's actually turned over. So you imagine a lot of rocks, they're all, this is the original surface. Well, now, if we were to just look at a section through here, this would be the youngest, same age as that one, right? But because we've bent it over, that means that we now have to use our geopedal structures to tell us which direction is truly up. You can look at this photo. It's got a nice fold in there, but it can get very complicated. You have to really pay attention to some of this stuff. Okay, here's our cross beds. Okay, and here are our mud cracks again. I just want to point out, what are these things? These little craters there. How do you form those? Rain? Yeah, they're just raindrop impressions. Are they a geopedal structure? Yeah, they don't form on the bottom of this, right? They form on the surface. So that tells us if we have our we got a surface like this and it's got a little drop like that, then we know this is the top, okay? And if we had this, then this would be the bottom down here, okay? So another geopedal structure. Okay, stromatolites. Stromatolites are kind of cool. They're actually formed by photosynthetic cyanobacteria, which we'll talk about these guys in the next module. But basically, they trap, they're a layer of these algae, if you want, and they trap sediment. And when they die, they all die on the bottom, you know, and float down to the bottom of this water, and they have sediment entrained in them, and they end up looking like these kind of squiggly lines. You can think about it, if you go out to the bayou sometimes, it's covered in like that green kind of slime, you know, think of it like that. That stuff dies, it's going to sink down, it's going to entrain sediment into it, and possibly get fossilized. Okay, concretion is also related to organism, the decay of organisms. And what happens is that minerals are precipitated out, and so you can end up with these concretions right there. Paleosol. I wondered for years why they called it a paleosol. Paleo is Latin for old, So anytime you hear paleo, it means old or ancient. And then solus is Latin, New Latin, for soil. And, you know, I used to wonder, I'd be in here teaching, you know, and I'll say, oh, they forgot to put the I in it. It should be paleo soil. But the reason they didn't is because of this word. So, paleosol, an ancient soil horizontal profile. If we think about it, we've got a surface out here, right? We've got soil covering the quad out here. Now, if we were to bring in a bunch of sediment and cover it up, okay, we could actually preserve that layer there. And that's what we're talking about here, a paleosol. They're commonly reddish or brownish red in color. This is because oxidation of iron-bearing minerals is going to supply this reddish color. So we can look here and got this nice reddish color indicative of oxidation of iron-bearing minerals. Oxidation is simply rusting. Okay, you leave your car out, your car rusts, basically, right? And so that's what's happening in our soils to our iron-bearing minerals. Okay, we have to interpret the lateral relationships between different environments. And we already talked about this a little bit. Volta's law of facies. I'll read you the actual definition. In an unbroken sequence, vertically superimposed lithofaces were laterally adjacent to each other at the time of deposition. How many understand that? Nobody? It's kind of difficult. We write things in a very difficult way sometimes. Remember this? All we're saying is that as sea level rises in this sequence, okay, our areas where we're depositing here, basinal clays, offshore silts, and then beach sands, those environments, as we increase sea level, are going to move onto the land, okay? And so we're going to get, eventually, this being deposited up here somewhere. So you end up with all these units, okay, on top of each other. And that predicts what was being deposited at any given time during our transgression. So we can just look at this sequence, okay, we know, if we have the geofield structures, we know that this would be the oldest and this the youngest. So we can take this, flip it over on its side, and that tells us what was being deposited at any given moment, okay, in our larger basin. Okay, so we have this idea of transgression, rise in sea level, submergence of the continent, and this occurs primarily part of the continental shelf, and we'll look at a cross-section of the ocean in a little bit. But then we get also sea level drop or regression, okay? Make sure you know what the two are, what they relate to. And having said that, do we have any more? Yeah. Just to let you know that these are all transgressions, okay? By definition, the word transgression. That's why that qualifier in there, historical geology. Otherwise, you could have selected either of those and you would have been correct. Okay, so let's look at our environments now. We've got three basic categories that we delineate. And we have non-marine, which are essentially on the continents, on land, okay? Then we have transitional. Sometimes they're referred to as marine, non-marine environments. These are the areas around the coastline where you get the interaction of the ocean and the land, okay, playing a part in those environments. And then the third one is marine, okay? So three basic categories of environments. Now, we have different environments within these, different subcategories, if you want, within each of these, and we'll look at some of those. Okay, the primary things we're going to look for when we're interpreting what kind of environment we have. Sediment types, okay? And that can be, you know, if we're looking at a rock, the grains in a rock are going to tell us what the sediment was. It's exactly the same, just been lithified. The fossils. Fossils are really useful in determining environments, right? If we were to, let's say, find a crab, a fossilized crab, what could we say about the environment? Sorry? Lived in water, right? Had to have lived in water. Where do we typically find crabs living in water? It's in that kind of transitional zone, right? We get them living in shallow marine environment. We get them sometimes in coastal swamp areas. So that gives us a really good idea of where we are, okay? So we have to look at these fossils and we have to make some inferences about them. But what we do is we look at the modern world. We look at animal species today and we see how similar they are to some of our fossils, and then we use that to interpret the environment. Okay, the other thing, we can use sedimentary structures. So if we had a crab fossil with symmetrical ripples in the same rock, what would that tell us? Beach, right? Beach. We can also use Volta's law of facies again to help us because of the type of sediment we've got. That can help us also. Okay, so let's look at non-marine environments. Freshwater fossils and terrestrial fossils. Okay, if we find T-Rex, you find the T-Rex, okay, doesn't have fins, right? Doesn't have any kind of fin structure, kind of more reptilian looking. Where would you say that lived? On the land, right? You're not going to say, oh, I think that lived in the ocean, right? It doesn't make sense for it to live in the ocean. So we can look at these fossils and we can actually start to build up a picture, okay, of whether we've got a terrestrial or non-marine environment rather than marine. Sediment colors. If it's reddish brown, that gives us an idea that it's oxygenated or oxidated. So it had to have been on the surface. And then erosional surfaces. We said last time, if you don't have land covered in water, then you're going to be eroding in some shape or form. Okay, one of the most significant environments, non-marine environments, the river. Okay. When we think about looking at the history of the planet, the fossils are very, very important. Now, you can get fossilization on dry land, but it's not that common because we have to bury a fossil or an organism with sediment very quickly, relatively quickly. We can do that in a river environment, but it's less common on the dry surface, okay? So this is some of the things we look for with this, with our river setting. Some of this can be preserved in the fossil record, or rock record I should say, how would we identify swamps? What kind of rock do we form in swamps? Nobody know?
Coal.
Coal, good. Very good. Coal. Coal is always formed in swamps, okay? We have a lot of vegetation. We go out, do a field trip and go hiking through the swamp. Is there a lot of vegetation out there? Absolutely, there's a lot of vegetation. What happens to that vegetation? It's going to die at some point, right? And it falls down, settles into that water. What happens to it then? Is that water moving very fast in that swamp? No, it moves
Still very
very still. And so it's not going to have a lot of oxygen in it. So that means that our plant material doesn't really rot away very well. It does decay, but not very much. It's compacted and compacted, and you end up with this, which is coal. Okay? All right. Here's an example of a river setting. This is what we call an incised meander. But notice you got this green, you got vegetation there, which means that there is some deposition going on in these rivers. Okay. Okay. Here's just a general outline of a river. Notice these former channels. Okay, where that river channel was flowing in the past. We can find these preserved in our rock record, which means that then we can identify that positively as a river or riparian setting. Riparian is just another word for river system. Okay, so if you ever hear the word riparian, you know we're talking about a river, river related. Okay, evidence in the rock record. We can find paleosols. Okay, so the former surface. Coal beds, plant fossils, symmetrical ripples. We can get symmetrical ripples in some cases, especially on land with wind gusts back and forth. Okay, that can create some symmetrical ripples, but only on very small particles. Concretions, graded beds, and levees. Okay, the levees are built up, they're natural on the side of a natural river system, so we're not talking about like the levees in around New Orleans or whatever. Okay, we're not going to talk really about freshwater stuff in this class very much, so it's there if you want it. I try to concentrate on the big picture in this class so we don't get tied up in minutiae. All right, alluvial fans. If you remember from physical, this is where you have a steep, very steep river, or it could be a dry channel, where that water's flowing very quickly. It's going to be able to carry large particles, but then it flows out onto a flat area, and that water just spreads out, loses its energy, drops everything that it's carrying, and we end up with our alluvial fan. Aeolian environments are just areas where wind is the predominant depositional agent. Sometimes, those sands which are blown by wind, very, very pretty. These are out in Utah, and some really interesting scenes from places like this. This occurs in the desert. Okay, commonly Aeolian environments are desert environments, but we can also find this on seashores. The dunes that run along the edge of a coastline are often affected by our wind. Okay, the glacial environment. Our glacial landscape, a lot of sub-environments, but we're not going to talk about all these different sub-environments. We're just going to look at glaciation as a whole, because it can actually tell us a lot about warming and cooling cycles on the Earth. Okay, And if we think about this, if we have a rock which is from the Precambrian, and we can identify some of this stuff, then that's going to allow us to say, well, we had an ice age at that point, right? If we can know the extent of some of these ice ages. So we look for these things: glacial grooves, moraines, eskers, drumlins, etc. And I got a graphic here which shows you. Okay, so hopefully it's a little bit of review. Got that glacial striations. So that ice, remember that ice flows. As it does, it picks up chunks of rock and it drags them across the bedrock, and you end up with these nice grooves. Okay. We don't know any other way of forming them, so if we find these, we're pretty sure that this area was glaciated at one point. If we can tell how old that is, then that's going to give us a clue to the climate on Earth at that point. Okay, eye clicker. Any more? Good job. Let's skip to. Right. Okay. Transitional environments. Transitional environments are very important because these can tell us where the coastline was. And if we know that, then we may be able to determine something again about the climate, right? Because if we can track where these transitional environments are at different times, we can tell if the sea level is rising or falling. So if we think about our continent like this, sea level's here, then our transitional environments are going to be here. If we raise that up, then our transitional environments are going to be up there. Okay, so very important for documenting cycles within the Earth. Some of our transitional environments are here: barrier islands, deltas, and salt flats. We'll talk about those in a minute. We can see here pictures of them. So here's our barrier island that runs through there. There's a delta right there. Why do we call this a delta? What is delta? What's that word mean? It's a Greek letter, right? What does the capital letter Greek delta look like? Triangle. So, why do we call that a delta? Does it look like a triangle? No, it doesn't, right? Well, it was actually named in Egypt, and the Nile in Egypt actually does kind of do something like this. So it looks like a delta. But the name stuck, you know, even though most of them don't actually look, have that triangular shape to them. All right, so when we're looking at coastlines, we can identify some features possibly in the rock record. We can have beaches, which means we're going to end up with sandstone, typically, not always. We can have these exposed marine terraces. Now, what's happening here is this is what we call an emergent coastline. What's the sea level doing? Dropping, right? The sea level is dropping, okay? And if we we call it emergent because it looks like the land is coming out of the ocean, okay? So, emergent, see these here, exposed marine terraces, formerly one of those, okay? And so, you raise the land up, you expose that wave cut platform, and it's going to be marine terrace. Let's see what else. Submergent, we can have tide islands and sea stacks. Estuaries. Estuaries are quite often good places for depositing relatively small sized particles, so muds and silts. Okay, our barrier islands. Barrier islands are really cool. Has anybody ever been to the Outer Banks in North Carolina? No? Really cool place to go. It's a national seashore. There's a lighthouse built on, it's a whole chain of barrier islands. And the lighthouse built there at Cape Hatteras on the Outer Banks in North Carolina. And a few years ago, several years ago now, they had to jack it up and move it because these barrier islands are incredibly dynamic places. They move back and forth. They don't stay in the same place, which really sucks if you're a human and you want to build a lighthouse, right? Because what's going to happen? Do you stop the island moving? No, you don't. It keeps moving, and it got so close to the ocean side of the barrier island that they actually jacked it up and moved it about 100 feet towards the lagoon side. Okay, so they don't stay where they are. They're very dynamic and primarily sand, long and narrow. So what might we find here? Let's think about fossils. What kind of fossils are we likely to find here? Seashells? How many people have walked along a beach? Yeah. So you should know that what would you find on the beach today? Well, you're going to see seashells, right? You should find maybe some dead seabirds, right? You might even find some fish. Fish sometimes die and wash up onto the beach. So you can find all sorts of different stuff to give you a clue that you're on this kind of beach environment here. We also have, if you can tie that beach into a lagoon on the back side of it, then that tells you got a barrier island, right? So here's some of our evidence down here. So here's our lagoon. So here's our barrier island. Here's our lagoon. We've got an estuary up there. So if we can find evidence for a beach and then some evidence of a lagoon or estuary, then that's going to give us a clue that we got a nice barrier island. What kind of water do you think we get in here? Fresh or salt water? Trick question, really, because it's mixed. You've got a river. Remember, estuary is a flooded river valley, so you've got fresh water flowing in, but then you've got salt water mixing there. And so our organisms living in that environment tend to deal with a wide variety of salinity levels. We actually call it brackish water. Periodically, during storms and stuff like that, seawater will actually flood in here, so it will actually increase the salinity. And then other times you might have a big storm on land, so you get a flood coming down the river, that's going to lower or decrease the concentration of salt. Okay, so brackish water, especially near the mounds. Lagoons, coastal lakes, okay, so we have to start thinking about how we would recognize some of these things. And then we can also get tidal flats. Tidal flats, mud or sand dominated zones, and they're exposed at low tide. Now, that's a very important. If you've ever been to a beach where the tide goes out a long way and exposes these wide um, tidal flats, you should probably have noticed that you'll see a lot of birds running around out there, and they dig up little shellfish and crabs and stuff like that that live under that mud below the surface. Very productive places. However, I'll just tell you a little story here. When I was young, my parents used to take me on vacation. We'd go down to a place on the coast of England called Brean Down, and the ocean, the tide, went out somewhere on the order of about 2 miles. And I, being who I am, I was always getting into trouble for wandering off. I go walking out there and tromping through the mud. The mud was up to my knees. And finally I, come back in, and there was this guy, and my knees are covered in mud all the way up to my knees. And the guy comes walking up and he says, "Do you know what that is?" I was like, "Yeah, it's mud." No, it's not. It's sewage. Since Victorian times in England, they dumped raw sewage into the ocean, and it basically just piled up out there. There is some natural mud there as well. They don't do it anymore. It's still, apparently, it's still very, very toxic. Sewage stays toxic for huge amounts of time. A neighbor, it was actually a friend's dad, back in Oxford, got a letter from the government telling him not to eat any vegetables grown in his garden because his garden was the site of a Roman latrine. So we're talking 2,000 years ago, and they're still picking up the bacteria from sewage in that. 2,000 years. Okay, so, be careful what you eat, I guess. All right, tidal flats. So these are sometimes very large areas. Okay, delta. We all know about deltas in this area, right? So you got the river coming down, and it deposits out on these lobes, and they change where it deposits all the time. We have something called what we call a deltaic sequence, a sequence of rocks that you can readily identify as deltaic. We'll look at that in a minute. And then we got these salt flats or subkas. And these occur at the margins of saltwater bodies where evaporation rates are high. What does that tell us? Hot. It has to be hot. An area that periodically floods with ocean water, but then temperature is high, and so it causes the evaporation, leaves the salt behind. So here's our deltaic sequence, just a stack. So we go from shale, silty shale, some siltstone, sandstone, and it may be back and forth like that. You're going to find different kind of fossils like this, okay? Excuse me. I point out that this one called seep earth is just a generic term. It's a British term. It's not used over here. But it's any sedimentary rock underlying a coal seam. So we have the coal here. So that's termed a seep earth. Okay, subka. Gypsum and halite. Primarily gypsum. We got gypsum, we got anhydrite, which is basically another form of gypsum. Okay, so primarily gypsum through there. So if we see this in the rock record, we know we've got a marine subka. All right. What did I do? Okay. Okay, anybody else? Good job. All right. Marine environments. Now, if we think about it, a large area of Earth is covered by ocean, right? 70%. So we get a very large amount of rock forming in because of the oceans. So we'll look at most important for our purposes are going to be the continental shelves, but we'll look at some of the other ones too. So here's a cross section of our ocean. We have the abyssal plain. This is really, really, really deep. Okay. Then we have a slight rise that's going up, what we call the continental rise. Then we get the continental slope, and then the continental shelf. Okay, if we're thinking about rock deposition, or deposition of sediments, build-up of rock, whatever you want to call it, what kind of rock do you think we're going to see formed on a continental shelf? Anything? Nothing? Well, no. Your transitional area is going to be right up here somewhere. So we're going to have limestone primarily forming offshore there on that continental shelf. What about the continental slope? Nothing? What did I tell you about submarine fens? Build up of sediment up here, falls off on a steep slope. Can you deposit sand on here? What's going to happen if a sand grain lands on that slope? It's just going to roll down, right? So we don't really see deposition there. We do at the base of it, we see these submarine fans and stuff like that. What about out in the deep ocean? What kind of sediment do you think we would get out there? Remember, it's really quiet water, very, very still. You get down, not very far down below this, and you're just going to be totally still, no effect from tide or anything like that. So very, very, very low energy. That's going to be our small mud particles, primarily what we're going to get out there. Why won't limestone form out here? There's a very good reason. If you have, let's say you have some shellfish swimming around up here, and he suddenly croaks and dies and sinks to the bottom. What happens to his shell? Does it land on the bottom? No. It's very still water. It's just going to sink down, right? It's kind of a trick question. Okay. Because there's something called the CCD, carbonate compensation depth. Now, this is the depth in seawater below which calcium carbonate will dissolve. So we go back here, a little shellfish, he died, and he sinks down. His shell is going to be eaten away in the deeper water. So fossils and stuff like that can't be deposited down here because of that. All right, let's see. Okay, any more? Good job. Okay, so we already talked about continental shelf. It's basically the area underlain by continental crust, not oceanic crust, and it's covered by marine water, and the extent depends on sea level position. So if we increase sea level, it's going to move it's going to expand that continental shelf area. We do have carbonate platforms. The Bahamas are a huge carbonate platform, and they have lots of different sub-environments. We have limestone and dolostone deposits and diverse marine fauna and flora. You know, Bahamas, you go out there, it's very popular to go scuba diving and stuff offshore because so much going on around these carbonate platforms. Stromatolites and thrombolites. We already talked about stromatolites. Thrombolites are very similar, but they occur in this kind of a mound kind of shape. Okay, here's our Bahamas banks, 8 kilometers thick. That's a pretty thick chunk of carbonate there. Okay, reefs. We have just basically a wave-resistant structure constructed by organisms, so corals and stuff like that. Famous one is the Great Barrier Reef, which is another incredible place to go if you ever get the chance. Relatively steep slope for the continental, so we don't really see much deposition occurring there. And then in the deep ocean, mud is the primary predominant sediment type. We call it, when we have sediment on the deep ocean, we call that pelagic sediment. Okay, just quickly I want to talk about this. We call this stable isotope analysis, and we use carbon and oxygen isotopes to look at the global temperatures through time. Now, this is an entire semester-long course to understand how this works, why it works, and how you do this. Now, in 2 slides, I can't communicate an entire semester, which I did take the course, and it is very complex. But you're going to have to trust me that this does work, okay? Basically, we can take limestone or glacial ice, and we can look at the oxygen isotopes in it. And we come up with something that we call delta O18, which is the ratio of different isotopes of oxygen. And it turns out that different temperatures relate to different ratios. So this delta O18 number, we'll come up with a number for that. And it will tell us whether, we can tell whether that oxygen came from inside the Earth, okay? We can tell whether it was rained out at certain temperatures. We have all this information. So with all this limestone that's built up out over the continental shelf for millions of, actually billions of years, we can use that to look at global climate, okay? And we don't just use one thing. It's one thing you gotta think about when you do science. You don't use one line of evidence. You know, you don't take your rock and say, oh, this was formed on a beach. You take your rock, you say, I think this was formed on a beach because this has sand, it's got beach fossils. So you don't just look at one thing. We use this in conjunction with many other things or processes to identify temperature. And it's a good thing to get that into your head, this multi-stance approach, because too often in real life we have 2 extremes and nobody thinks about what's in between. You know, we always hear this term, oh, the issue is black or white. The issue, I don't know, creation versus evolution. These are extremes. Democrat, Republican, okay? Most people actually fall in the middle on those issues, right? And this, we get trapped into this this thinking of just being bimodal. We just got two extremes. So you have to start thinking more like a scientist, where you start to say, okay, got this on one end, this on the other, I might be somewhere in the middle. And so start thinking along those lines, and everything should work out. All right, eye clicker and we'll get out of here. Any more? Good job. All right, get out of here. We'll see you on Wednesday.
What did you say about glacial environments?
One moment.
It wasn't really on the slide.